Welcome back, everybody. Today we're going to talk about the fundamental theorem of calculus. All right, so in the last couple sections we did integration using sigma notation. We found it pretty cumbersome, lots of algebra, takes lots of time, hard to set up. So there must be a better way. Well, Isaac Newton and Gottfried Leibniz independently both came up with a better way to do this. It is called the fundamental theorem of calculus. And basically what happens is that you do the integral from a to b of f of x, right? You do the antiderivative, right? And you plug in your upper limit, right? Antiderivative, plug in your lower limit. Now this must be continuous, smooth curve on an interval in order to work. So let's jump right in to some examples. Integrate from 1 to 2, x squared minus 3 dx. All right, so we're going to split this up. I'm going to do the integral from 1 to 2 of x squared minus the integral from 1 to 2 of 3. Right, and there's both a dx in there. Right, let me just put the dx's in there. All right, so then you do the antiderivative, and I get x cubed over 3 from 1 to 2 minus 3x from 1 to 2. Now we're going to plug in our upper limit. So I plug in 2 and I get 8/3 minus 1/3. Right, that's upper limit minus lower limit. Minus 6 minus 3. Upper limit minus lower limit. 8/3 minus 1/3 is 7/3. 6 minus 3 is 3. And when I do the subtraction, I get negative 2/3. All right, we teased this in a prior video, but what I'd like to do is do a lot of practice in order to get the feel for what's going on. So let's do another example. So I'm going to do the integral from 1 to 4 of 3 square root x dx. Now for this one, I like to start by just rewriting it. 3x to the 1/2 power, because if I have the 1/2 power, then I'm better able to do my power rule for my power rule for integration. I can bring the 3 out. X to the 1/2. All right, so now I want to do the antiderivative of x to the 1/2. So I have 3 times x to the 3/2 divided by 3/2, right? And so that would be simplified, would be 2x to the 3/2, and that's between 1 and 4. All right, so at this point, we're going to execute the first fundamental theorem of calculus. I'm going to plug in the 4 and then plug in the 1. So I have 2 times 4 to the 3/2 minus 2 times 1 to the 3/2. So why don't you at this point pause the video, do the last little bit of work, and then we will correlate our answer on the back end. All right, so I got, this was 16 minus 2, so I got a total of 14, and that should be your answer. All right, it wouldn't be one of my videos unless we did at least one with trig, so I'm going to go from 0 to pi over 4 of, I'm going to put secant squared x dx. So when you think about this, what you need to think about is what trig function has a derivative of secant squared. And there's your integral. So this is going to be tangent x from 0 to pi over 4. So I do tangent pi over 4 minus tangent of 0. And that's 1 minus 0, which equals 1. So you look at a trig problem, and as long as you can ask yourself the right question, so for example, in this case, it is what trig function has a derivative of secant squared? And because you know your derivatives, you know that tangent has a derivative of secant squared. It becomes a much, much easier integral to do. All right, so at this point, the only thing to do is to practice a variety of different examples. These examples can come in different forms. So here is another way you could see an example. Find the area of the region bounded by the graph, y equals x squared minus 3x plus 2, between the x-axis and vertical lines x equals 0 and x equals 2. Well, on the graph, if x equals 0 is here and x equals 2 is over here, certainly seems like limits of integration. So I'm going to integrate from 0 to 2, and then my function is 2x squared minus 3x plus 2. All right. So let's do my antiderivative. So actually, you know what? You guys are experts at the power rule for integration. Why don't you pause the video and you guys do take a run at the antiderivative, and then we'll work on the fundamental theorem when we get back. All right, so I got 2/3 x cubed minus 3/2 x squared plus 2x between 0 and 2. And people put a variety of things. Some people put a bracket. I put a line. It's just the way the guy who taught me did that. But now we need to plug 2 in to our function, and we need to plug 0 into our function. So again, I'm going to ask you to pause the video. Let's plug 2 in and plug 0 in, and we'll talk about the answer on the back end. Okay, so I got, let's see, so it's 2 plugging in 2 here, that's 8. 8 times 2 is 16/3. 2 squared is 4. 4 times 3 is 12, so that's minus 12/2 or 6. And 2 times 2 is 4, so plus 4. So that's plugging in your upper limit, and I'm going to subtract my lower limit. So I'm going to plug in 0 minus 0, 0 minus 0 plus 0. I love when you have 0 and everything is multiplied. So 16 minus 6 plus 4, I got 10/3. Hopefully you got the same thing. All right, so one of the applications of integrals, and especially the definite integral, is we can use a defined average value. So for average value, here is our formula. 1 over b minus a, the integral from a to b of f of x dx. All right, so the b minus a, the b and the a are still the upper and lower limit of integration. So that's where they come from. But this is the basic formula that you're going to use anytime you see something that says something like this. Find the average value of f of x equals 3x squared minus 2x on the interval (1, 4). All right, so let's use this formula to set it up. I'm going to scroll up right now because I'm assuming you have the formula written down. So we do 1 over b minus a, 4 minus 1, times the integral of from 1 to 4 of 3x squared minus 2x. Always dx there, that is important. So that would be 1/3 times the integral from 1 to 4 of 3x squared minus 2x dx. All right, so let's do our antiderivative. So I'm going to scroll up a little bit. I get 1/3. That's still a constant, comes along for the ride. Now my integral, I get x cubed minus x squared. Hope you got the same thing. Between 1 and 4. 1/3. Let's plug in. So 4 cubed is 64 minus 16 minus 1 minus 1, which obviously 1 minus 1 is 0. So 64 minus 16 is 48, so it's 48 over 3, which equals 16. All right, so that's the first fundamental theorem of calculus. And now we're going to take a look at the second fundamental theorem of calculus. All right. So second fundamental theorem is not nearly used nearly as much as the first, but it pops up on occasion. So the second is the derivative of the integral between 0 and x of f of t dt equals just f of x. Sorry about that. All right, so let's do a quick example. The derivative of the integral between 0 and x of square root of t squared plus 1. All right, so the origins of the second fundamental theorem basically come through the chain rule. You don't necessarily need to know all the steps. All you need to know is that when you're integrating from 0 to x and taking the derivative, that you get x squared plus 1 instead of t squared plus 1. So, and I am not expecting any other work to be shown. All right. All right, I have one last example that I want to show you, and it kind of combines the chain rule and the second fundamental theorem. Find the derivative of I'm going to do it on the next line. I'm not going to get enough room. So I'm going to say big F of x equals the integral from pi over 2 to x cubed cosine t dt. All right, so we're going from a number to x cubed, and I'm finding the derivative of the integral. Sounds like second fundamental theorem to me. However, we're not just going to x, we're going to x cubed. So we're going to use the chain rule, and I'm going to say that u equals x cubed, du equals 3x squared dt. So if I'm looking for the derivative of f prime of x, that's going to be the derivative of f in terms of u times the derivative of u in terms of x. So there's your chain rule. So this is going to equal the derivative of the integral from pi over 2 to x cubed of cosine t dt times du dx. Right? So here's df du, and there's du dx. So I use my second fundamental theorem on the first piece, and I wind up with cosine. Now I take this top part, it's going to substitute in, and I get x cubed and du dx. Right? Du dx, that's not a dt, that's a dx down here. Is 3x squared, that's my fault, times 3x squared, and there is your substitution. And typically we write the algebraic part first, 3x squared times cosine x cubed. All right, guys, this was a short one. Again, we had teased the first fundamental theorem in a prior video as well. So just doing a little bit of practice to make sure that you're getting it, and to check out the second fundamental theorem. Again, the second fundamental theorem, not nearly used as much. However, it does pop up on occasion. All right, guys, thanks for listening, and I'll see you soon.